close your eyes for just a moment. Somewhere out there, right now, beyond every star you have ever named, an intelligent civilization may be staring into the same darkness you are staring into tonight, wondering, searching, asking the exact question sitting quietly in your chest right now. But here is the thing nobody wants to hear. They are never coming, not because they do not exist, but because the universe itself, the very fabric of space and time and energy, has built walls around every living world, so absolute, so mathematically brutal, that no amount of intelligence, no amount of technology, no amount of determination can break through them. Tonight, we are going to walk up to those walls together. We are going to press our hands against them. We are going to feel exactly how thick they are, and why nothing, not even the most advanced civilization imaginable, has ever crossed them to find us. This is not a story about whether aliens exist. This is a story about why the universe will never let them reach us, and by the time it is over, you will never look at the night sky the same way again. If this is the kind of journey you want to take every night, like this video and subscribe. Now, settle in, get comfortable. We begin. Look up tonight. Find two stars that seem close together. Maybe they sit side by side like twin diamonds pressed into dark cloth. Your eyes tell you they are neighbors. Your brain says they are near each other, separated by just a small gap of black sky. This is a lie, and it is the oldest lie the universe has ever told. Those two stars might be separated by 50 light years. One might be a small, dim red dwarf sitting just 6 light years from Earth. The other might be a blazing blue giant burning 800 light years away. They are not neighbors. They are not even in the same part of the galaxy. But from where you stand, barefoot on cool grass, tilting your head back on a clear night, they look like they are touching. The sky has taken the most unimaginable distances in all of nature and crushed them flat. It has folded trillions upon trillions of miles into a simple dark ceiling decorated with tiny points of light. And your brain, that beautiful but limited organ, has done what it was built to do. It has made the impossible look manageable. This is not your fault. Your eyes were never designed for this job. Human vision evolved on the plains of Africa, where the most important distances were measured in feet and miles. How far away is that predator? How wide is that river? Can I throw a rock that far? These were the questions that shaped your visual system over hundreds of thousands of years. Your ancestors survived because they could judge short distances with speed and accuracy. Nothing in that long history of survival prepared your eyes, or any eyes, to understand what a light year actually means. So, when you look up at the stars, your brain uses the only tools it has. It flattens, it simplifies, it turns the most terrifying emptiness in existence into something that looks like a painting on a ceiling. And here is what matters. Every civilization that has ever looked upward has been fooled by this same trick. Not just us. Every thinking being on every world, orbiting every star in this galaxy, has gazed at their own sky and seen the same comforting illusion. Stars that look close, distances that look crossable, a universe that looks like it was made to be explored. The sky does not whisper warnings. It whispers invitations. Come, it says. The lights are just over there. You could almost reach out and touch them. You cannot. The Pacific Ocean is the largest body of water on Earth. It stretches roughly 11,000 miles at its widest point. If you could somehow lay the Pacific Ocean end to end across the gap between our sun and the nearest star, you would need to do it more than 2 billion times. 2 billion Pacific Oceans is placed one after another in a line that stretches so far, the human mind simply gives up trying to picture it. And that line would carry you only to the closest star. not to a distant star, not to an interesting star, just to the front door of our nearest neighbor in a galaxy that contains 400 billion other doors. This is the truth the sky hides from you every single night. The stars are not destinations on a map. They are not cities connected by roads. They are tiny islands of light floating in an ocean of nothing. And that ocean is so wide that the word ocean does not even begin to describe it. We use the word because we have no better one, but the comparison is almost meaningless. The real distances between stars exist in a place beyond human language, beyond human feeling, beyond anything your senses were ever built to understand. There is an old thought experiment that scientists sometimes use to help people feel the scale. Imagine shrinking the entire Milky Way galaxy down to the size of the United States, coast to coast, border to border. At this scale, every star becomes a grain of fine dust. Our Sun and Alpha Centauri, the closest star system, would be two tiny specks sitting about 4 inches apart. That seems close enough to reach, but the next sun-like star with a planet that might support life could be several feet away. A civilization 1,000 light years from us would be located in a completely different state, and the far edge of the galaxy would be on the opposite coast. The galaxy looks crowded on a poster. It looks full of possibility on a computer screen. But in reality, most of that map is blank. Most of that space contains absolutely nothing. The emptiness between those tiny grains of dust is the true character of the galaxy, not the stars, the silence between them. And here is something strange that most people never consider. Some scientists have speculated that this very illusion, the flatness of the night sky, might be a kind of cosmic filter. Not a physical barrier, but a psychological one. It gives every young civilization the false confidence to dream about reaching the stars, which drives them to develop science and technology. But once they do the real math, once they truly understand the distances involved, many of them might simply stop trying. The dream that pulled them forward was based on a lie, and discovering that lie might be one of the great silent heartbreaks that every intelligent species in the universe eventually faces. This idea lives on the fringe of astrobiology, but it carries a strange, sad poetry. The sky inspires you to reach for the stars. The math tells you they were never within reach at all. There is also a genuine scientific debate hiding inside this illusion. Astronomers still argue about how to accurately convey cosmic distances to the human mind. Some researchers in science communication believe that our traditional ways of describing space, using numbers like light years and parsecs, actually make the problem worse. These units sound tidy, they sound manageable. 4.24 light years to the nearest star. You can say that in a breath, but that single number hides 25 trillion miles of empty void. Some scientists have proposed new methods of visualization, scaling the solar system down to physical models people can walk through, so that the distances become something you feel in your legs rather than just read on a page. The debate is not settled. We still do not have a good way to make human minds truly grasp how far away the stars really are. And until we do, the old lie continues to work its quiet magic every clear night. This matters deeply for the question we are exploring together tonight, because when someone imagines aliens traveling to Earth, they are imagining a journey. A long one, yes. A hard one, absolutely. But still a journey, with a beginning and a middle and an arrival. The night sky encourages this thinking. It makes the trip seem possible. It frames the stars as places you can go to, like distant cities on a globe. But the space between those stars is not a road. It is not even a wilderness. It is a void so vast and so empty that the very concept of travel begins to lose its meaning inside it. And that void, that staggering silent emptiness between one grain of dust and the next, is where our story truly begins to deepen. Because the distance is not just large, it is large in a way that changes everything. Let us put a number on that void. Let us try, even though the number itself will fight against your ability to feel it. The closest star system to our Sun is Alpha Centauri. It sits 4.24 light-years away. Say that number out loud. 4.24. It takes less than a second to speak. It sounds small. It sounds like something you could handle. But a light-year is not a friendly unit of measurement. It is a mask that hides something enormous behind a simple label. One single light-year equals roughly 5.88 trillion miles. Now, multiply that by 4.24. Alpha Centauri sits approximately 25 trillion miles from where you are right now. 25 trillion. If you started counting to 25 trillion, speaking one number every second without ever stopping to sleep, eat, drink, or rest, you would need nearly 800,000 years to finish. You would begin your count before modern humans had fully spread across Africa. And every pharaoh would rise and fall while you counted. Every empire would build its great monuments and crumble to dust. Every war in every history book would be fought and forgotten. And still you would be counting. Still nowhere close to done. That is the distance to the nearest star. Not a far star, not a special star. The closest one. The galactic front door. Now, let us see how humans have actually performed against this distance. In 1977, NASA launched Voyager 1. It is the farthest human-made object from Earth. Voyager travels at roughly 38,000 miles per hour. To feel how fast that is, think of a bullet fired from a powerful rifle. That bullet moves at about 1,700 miles per hour. Voyager is roughly 22 times faster than that bullet. It has been flying outward for more than 4 decades without stopping, without slowing, without turning. In all that time, Voyager 1 has covered about 15 billion miles. And 15 billion miles sounds like it should mean something. It sounds like a serious distance. But measure it against the interstellar scale and it becomes almost nothing. 15 billion miles is less than one single light day, not one light year, one light day. The distance that light covers in just 24 hours. And a light day is just 1/365th of a light year. And the nearest star is over 4 light years away. At its current speed, a Voyager 1 would need approximately 73,000 years to reach Alpha Centauri. 73,000 years. The entire stretch of human civilization, from the first farming villages in Mesopotamia to the phone in your hand, covers roughly 12,000 years. Voyager would need 6 times that entire history just to reach the house next door. And here is the part that quietly breaks your heart. When Voyager finally arrived, it would not stop. It carries no braking system. It would sail past Alpha Centauri like a whisper past a window and continue into the emptiness beyond. A frozen relic tumbling through darkness, carrying a golden record full of human music and greetings that no one would ever play. It would become cosmic debris, slowly cooling to the background temperature of space, forgotten by a species that might not even exist anymore by the time it gets there. Now step back further. Alpha Centauri is 4.24 light years away. Sirius, the brightest star you can see in the night sky, sits 8.6 light years out. That is roughly 50 trillion miles. Vega, a star you might recognize from summer evenings, is 25 light years away, about 147 trillion miles. Betelgeuse, the red giant that marks the shoulder of Orion, lies around 700 light years from Earth. And converting that distance into miles gives you a number so long it would stretch across your entire screen. And all of these stars are inside our own galaxy. They are not exotic objects at the edge of the observable universe. They are just ordinary neighbors in our local stretch of the Milky Way, and the distances between them already make Voyager's 4-decade journey look like a single footstep at the start of a walk across a continent. The Milky Way itself spans approximately 100,000 light-years from one edge to the other. That is roughly 588 quadrillion miles. Our solar system sits about 26,000 light-years from the galactic center, tucked into a small spur of the Orion Arm, about 2/3 of the way out from the core. Light leaving one side of the galaxy needs 100,000 years to reach the other side, not a spacecraft. Light, the fastest thing in the universe, the absolute speed limit that nothing made of matter can ever reach. Even light, moving at 670 million miles per hour, needs 100,000 years to cross our single galaxy. A human lifetime is roughly 80 years. Light crosses the galaxy in a time equal to 1,250 consecutive human lifetimes laid end to end. Each of those lifetimes would begin and end in total darkness between stars, surrounded by nothing, with the destination no closer to the eye than it was at the start. Here is a fact that sits on the edge of current scientific debate. Some astronomers have recently begun arguing that even our measurements of interstellar distances carry small but meaningful uncertainties. The Gaia Space Telescope, launched by the European Space Agency, has been mapping the positions and distances of over 1 billion stars with extraordinary precision, and its data has revealed that some stars we thought we knew well are slightly farther or closer than previous estimates suggested. The distances to nearby stars are not perfectly settled science. They are being refined right now, in real time, as new data streams in. The numbers we use today are very good, but the universe keeps reminding us that even measuring the gap is harder than it looks. And there is one strange, speculative idea that deserves a quiet moment here. Some thinkers have wondered whether the sheer scale of interstellar distance might itself be a kind of answer to the famous Fermi paradox, the question of why we have never detected alien civilizations. Not because aliens are rare, but because the distances are so extreme that even a galaxy teeming with intelligent life would appear completely silent. Every civilization trapped on its own island. Every signal too faint to detect. Every journey too long to complete. The silence of the cosmos would not mean we are alone. It would mean we are separated, isolated by a geography so vast that togetherness becomes physically impossible. The universe might be crowded with minds and still sound perfectly empty. This is the foundation that everything else rests upon. The distance is not a problem to be solved. It is a condition to be understood. It shapes every question we can ask about whether aliens could ever reach Earth. It turns the idea of a journey into something almost unrecognizable. Because crossing 25 trillion miles is not a trip. It is not even an expedition. It is something for which human language does not yet have a proper word. And the space that fills those trillions of miles, the actual substance of the void between one star and the next, is itself a place so strange and so hostile that it deserves its own careful look. You have now felt the distance. 25 trillion miles to the nearest star. Hundreds of trillions to the next ones beyond that. But distance is just a number until you understand what fills that distance. Or rather, what does not fill it. Because the space between stars is not like any emptiness you have ever experienced. It is not the emptiness of a dark room. It is not the emptiness of a desert at midnight. It is an emptiness so complete so perfect, are so total that it makes every empty place you have ever known feel crowded by comparison. Scientists call it the interstellar medium. The name sounds almost cozy, as if it were a substance, a kind of thin cosmic air connecting one star to the next. It is not. The interstellar medium has a density of roughly 1 atom per cubic centimeter, one single atom floating alone in a space the size of a sugar cube. To feel what that means, consider the air you are breathing right now, as every cubic centimeter of that air contains approximately 25 quintillion molecules, 25 followed by 18 zeros. The interstellar medium is roughly 25 quintillion times less empty than the breath sitting in your lungs at this moment. It is a vacuum more perfect than anything humans have ever created in any laboratory on Earth. If you gathered all the atoms scattered through a cubic mile of interstellar space, and you would not have enough material to fog a mirror, and it is cold. Not cold the way winter is cold, not cold the way the dark side of the moon is cold. The interstellar medium hovers just a few degrees above absolute zero, the temperature at which all molecular motion nearly stops. Absolute zero is minus 273 degrees Celsius. The void between stars sits at roughly minus 270 degrees. At this temperature, the concept of warmth has no meaning. Heat is a memory from another place. The cold does not bite. It does not sting. It simply is. It surrounds everything, touches everything, and waits with infinite patience for anything warm to surrender its energy and go still. It is also dark. Not the darkness of a room with the lights off, where your eyes adjust and shapes slowly emerge. In the interstellar void, there is nothing for your eyes to adjust to. The nearest star might be trillions of miles away in every direction. Its light, by the time it reaches you, is so faint that it would not illuminate the palm of your hand held an inch from your face. You would float in a blackness so absolute that the difference between having your eyes open and having them closed would be nothing. No landmarks, no horizons, no reference points. No way to tell if you are moving or still. No way to feel the passage of time except by watching a clock whose ticking would be the only proof that the universe had not simply stopped. This is the road between the stars. This is what any traveler, human or alien, must cross. Not a highway through interesting terrain. Not an ocean with waves and weather and the occasional island. A void so empty that the word empty becomes almost meaningless. A place where nothing happens, where nothing exists, where the nearest significant object in any direction is trillions of miles away. A spacecraft traveling through this medium would spend decades or centuries surrounded by absolutely nothing. The silence would not be poetic. It would be structural, built into the fabric of the space itself. And that emptiness creates a problem that goes beyond loneliness. It creates a problem of navigation. Finding your way across interstellar distances requires a kind of precision that has no parallel in human experience. When you drive across a country, you follow roads, you read signs, you check maps against landmarks you can see with your own eyes. In the interstellar void, there are no roads, no signs, and no landmarks. There is only the destination star, a tiny point of light among billions of similar points, and the mathematics that tells you how to aim for it. The precision required is staggering. At the scale of light years, even a tiny error in your direction at the start of the journey grows into an enormous miss at the end. A navigational error of just 1/10,000th of a degree at departure translates into missing your target star system by billions of miles at arrival. Not thousands of miles, not millions, billions. That is the difference between reaching a solar system and sailing past it into empty space with nothing ahead of you and no possibility of turning around. Because turning around requires energy. Energy requires fuel. And fuel is mass that you have already spent everything to accelerate. Every course correction during the journey burns fuel that was budgeted for the trip itself, and every kilogram of extra fuel you carry demands even more energy to accelerate in the first place. The mathematics loops back on itself like a trap with no exit. Here is a fact from the edge of current science that makes this even more unsettling. Astronomers have discovered that the interstellar medium is not perfectly uniform. It contains regions of slightly higher and lower density, vast bubbles blown by ancient supernova, thin streams of gas shaped by magnetic fields, and clouds of molecular dust that drift slowly through the galaxy over millions of years. Our own solar system currently sits inside something called the local bubble, a region of unusually low density gas that was carved out by a series of supernova explosions roughly 10 to 20 million years ago. A spacecraft traveling to another star would pass through these varying regions, each with slightly different conditions, slightly different particle densities, slightly different magnetic environments. The void is not even consistent in its emptiness. It shifts and changes in ways that would be invisible to any traveler passing through at high speed. There is also a speculative idea that some researchers have quietly discussed in the margins of astrobiology conferences. What if the interstellar medium itself acts as a kind of natural barrier, not just through its emptiness, but through what it does to anything that tries to cross it at high speed? At velocities that are even a small fraction of light speed, the sparse hydrogen atoms scattered through interstellar space stop being harmless. They become tiny projectiles, each one striking the front of a spacecraft with energies that accumulate over years and decades of flight. Some theorists have wondered whether there exists a practical speed limit set not by Einstein's equations, but by the interstellar medium itself. A velocity above which no material, no matter how strong, can survive the slow sandblasting of trillions of atomic impacts over the course of a multi-decade journey. This idea is not proven. It is debated. But it carries a haunting suggestion. The void between stars might not just be empty. It might be actively hostile to anything that dares to cross it quickly. And here is the quiet truth that sits beneath all of this. The interstellar medium does not care about your mission. It does not care about your technology. It does not care whether you are human or alien, biological or mechanical, ancient or young. It simply exists, cold, dark, empty, patient. It has been sitting between the stars for billions of years, unchanged, unmoved, and completely indifferent to anything that tries to pass through it. It will be there long after every civilization in this galaxy has risen and fallen and been forgotten. The void does not fight you. It does not resist you. It does something worse. It ignores you. And in that ignorance, in that perfect cosmic indifference, it becomes the most dangerous terrain any traveler could ever face. But even if you could somehow cross that emptiness, even if you could navigate those trillions of miles with perfect precision through perfect darkness, there remains a question that comes before the journey itself. A question that most people never think to ask. How would anyone out there even know we are here before any alien civilization could ever travel to Earth? They would first need to know Earth exists. This sounds obvious. But the reality of how invisible our planet truly is from interstellar distances is something most people have never seriously considered. We think of Earth as important, as special, as the bright blue jewel of our solar system. And from our perspective, it is. But from the perspective of a civilization orbiting a star even a few hundred light years away, Earth is nothing. Not uninteresting, not overlooked. Nothing. Invisible in almost every way that matters. Start with the simplest question. Could they see us? Earth is a small rocky planet with a diameter of roughly 8,000 miles. It orbits an unremarkable yellow dwarf star in the outer suburbs of an ordinary spiral galaxy. From even a few light years away, Earth reflects such a tiny fraction of the sun's light that it vanishes completely against the glare of its parent star. Imagine trying to spot a firefly hovering next to a lighthouse from 1,000 miles away. That is roughly the challenge of directly observing an Earth-sized planet orbiting a sun-like star from interstellar distances. The star outshines the planet by roughly 1 billion to 1. The planet is simply swallowed by the light of its own sun. Could they detect Earth indirectly? There is a method astronomers use called the transit technique. When a planet passes in front of its star from the observer's point of view, it blocks a tiny sliver of starlight. That dip in brightness can reveal the planet's existence, its size, and sometimes even hints about its atmosphere. This is how NASA's Kepler mission discovered thousands of exoplanets. But the transit method has a cruel limitation. It only works if the planet's orbital plane happens to line up precisely with the observer's line of sight. The geometry must be nearly perfect. For most observers scattered around the galaxy, Earth's orbit does not align this way. From their angle, Earth never crosses the face of the Sun. It simply orbits invisibly, hidden by the geometry of its own path. For the vast majority of possible alien civilizations, Earth cannot be detected by this method at all. What about our atmosphere? This is perhaps the strongest card Earth holds. Our atmosphere contains oxygen at levels that are unusual for a rocky planet. Oxygen is a reactive gas. It wants to combine with other elements. Left alone, it would disappear from an atmosphere within a few million years. The fact that Earth's atmosphere maintains high oxygen levels is a sign that something is actively producing it. That something is life. Photosynthetic organisms, plants and algae and cyanobacteria, continuously pump oxygen into our atmosphere, keeping it at levels that would not exist on a dead world. An alien civilization with extremely powerful telescopes might, in theory, detect the spectral signature of oxygen in Earth's atmosphere by analyzing the thin sliver of starlight that passes through our air during a transit. But detecting these faint chemical fingerprints across hundreds of light years pushes the limits of any conceivable telescope technology. The signal is extraordinarily weak. It would require instruments of a scale and sensitivity that even our most optimistic engineers struggle to imagine. And even if they detected oxygen, they would not know there is intelligent life here. Oxygen suggests biology. It does not suggest civilization. They would see a world that might have forests and oceans and bacteria. They would not see cities or roads or radio towers. From 1,000 light years away, Earth with its oxygen atmosphere looks exactly the same as Earth looked 3 billion years ago, when the only life was single-celled organisms floating in ancient seas. Biology and civilization produce very different signals, and only one of those signals is detectable at interstellar distances. The other is invisible. Now consider radio. This is the detection method that most people think of first. Humanity has been broadcasting radio signals since the early 20th century. Television, radar, satellite communications, all of these produce electromagnetic radiation that leaks into space at the speed of light. These signals expand outward from Earth in a growing shell, reaching farther into the galaxy with each passing year. That shell of radio emissions is currently roughly 200 light-years in diameter. It encompasses perhaps a few 100,000 stars. This sounds like a reasonable number until you compare it to the 400 billion stars in the Milky Way. Our radio bubble covers less than 1/millionth of the galaxy's volume. Beyond that thin shell, Earth is electromagnetically silent, completely invisible. A civilization sitting 1,000 light years away has received nothing from us. Our signals will not reach them for another 800 years, and they have no other way to know we are here. But even within that 200 light-year bubble, detection is not guaranteed. It is not even likely. Radio signals weaken with distance according to a rule called the inverse square law. When you double the distance, the signal becomes 4 times weaker. Triple the distance, it's 9 times weaker. By the time Earth's strongest radio broadcasts have crossed even 100 light years, they have spread across such an enormous volume of space that the energy arriving at any single point is vanishingly small. Distinguishing that faint whisper from the natural radio noise of the cosmos, the hiss of stars, the pulse of pulsars, the crackle of cosmic background radiation, would require receivers of a size and sensitivity that borders on the impossible. This detection problem works in both directions. If alien civilizations are broadcasting their own signals, those transmissions weaken by the same law. A powerful alien broadcast crossing 500 light years would arrive at Earth as a signal billions of times fainter than the background noise of space. We would not hear it, not because we are not listening, we are. Programs like SETI have been scanning the skies for decades, but the signals, if they exist, are simply too faint, too diluted by distance, too buried in cosmic static to be pulled out of the noise. Here is something that sits right at the edge of scientific debate. Some researchers have proposed that laser communication might offer a more focused and detectable alternative to radio. A powerful laser aimed directly at a target star could concentrate its energy into a tight beam, rather than spreading it in all directions. This would make the signal far stronger at the receiving end, but it introduces a new problem. A laser must be aimed precisely at the right star. The sender must already know where to point. They must already know someone is there. Which brings us back to the original problem. They cannot know we are here because they cannot see us. And here is a strange, speculative thought that haunts the edges of this discussion. What if the universe is full of civilizations that are all listening, but none are transmitting? Each one afraid to reveal itself, or each one waiting for someone else to speak first. This idea, sometimes called the dark forest hypothesis, suggests that the galaxy might be a quiet place, not because it is empty, but because everyone is hiding. It is an unproven idea, but it adds another layer of silence to a cosmos that already seems determined to keep its inhabitants apart. From 1,000 light years away, everything humanity has ever built or broadcast or dreamed is one anonymous dot among 400 billion similar dots. We are invisible. We are silent. We are lost in a crowd so vast that being found is not just unlikely, it borders on miraculous. No civilization is coming to find us because no civilization can find us. The universe is keeping our existence a secret, and it is doing so not through any grand design, but through the simple, is brutal arithmetic of distance and the speed of light. They cannot see us. They cannot hear us. They do not know we exist. But suppose, against all odds, they did. Suppose they somehow identified Earth as a world worth visiting. They would then face a cost so staggering that knowing where to go would be the least of their problems. Suppose they found us. Suppose some extraordinary civilization, 1,000 light years away, somehow detected Earth's faint oxygen signature, somehow guessed that intelligent life walks its surface, and somehow decided this tiny blue world was worth the trip. The destination is chosen. The will is there. Now they must pay the price. and the price the universe demands for moving anything between stars is so enormous, so fundamentally staggering, that it makes every other obstacle we have discussed feel like a gentle introduction to the real nightmare. The only way to shrink an interstellar journey from geological ages into something even remotely approachable is speed. And speed at the scales required for star travel costs energy in quantities that would bankrupt entire worlds. This is not a soft barrier. This is not a challenge that a bigger engine gradually solves. The energy requirements for interstellar travel grow in ways that are fundamentally hostile to any engineer, on any world, in any era. They do not grow steadily with speed. They grow exponentially. And that exponential curve is not a feature of anyone's current technology. It is a feature of the universe itself, written into the equations of special relativity, confirmed by every particle accelerator ever built, and inescapable for any civilization made of matter anywhere in the cosmos. Let us ground this in real numbers. To travel between stars in anything shorter than tens of thousands of years, a spacecraft must reach a significant fraction of the speed of light. 10% of light speed is a common benchmark in serious discussions about interstellar travel. At this velocity, a ship would move at roughly 67 million miles per hour. That is almost 18,000 miles every single second. For perspective, the Parker Solar Probe, the fastest human-made object ever built relative to the Sun, reaches approximately 430,000 miles per hour at its closest approach. 10% of light speed is more than 150 times faster than the fastest thing humanity has ever created. This is not a matter of building a slightly better engine. This is a matter of entering an entirely different world of physics. Now consider what it takes to push something to this speed. Start with something small. Not a crude vessel, not an ark carrying colonists, just a robotic probe. Instruments, a communication system, a power source, and a frame to hold it together. Call it 1,000 kilograms, roughly the mass of a small car. To accelerate this modest machine to 10% of light speed requires approximately 450 quadrillion joules of kinetic energy. That number floats in the air like an abstraction, so let us anchor it to something you can feel. A large nuclear power plant produces roughly 1 gigawatt of continuous power. 1 billion joules every second. Running that single plant at full capacity for an entire year produces approximately 31.5 petajoules of energy. So, accelerating our tiny car-sized probe to just 10% of light speed would consume roughly 14 years of that nuclear plant's total output. 14 years of a facility that costs billions of dollars to build and powers 1 million homes. Every watt, every joule are funneled entirely into pushing one small object to a velocity that still means a 42-year trip to the nearest star. Widen the lens further. The total energy that all of humanity produces in an entire year, from every power plant, every engine, every fire, every solar panel on the face of the Earth, amounts to roughly 580 quintillion joules. The energy needed to accelerate our tiny 1,000 kilogram probe to 10% of light speed is approximately 1/300th of that global annual total. 1/300th of everything the entire human species generates in a year, for a single probe, with no crew, no life support, no way to slow down when it arrives. Just a small machine thrown into the darkness with enough speed to reach the nearest star in 4 decades. Here is another way to feel it. The atomic bomb dropped on Hiroshima released approximately 63 trillion joules of energy. The kinetic energy of our modest probe at 10% of light speed equals roughly 7,000 Hiroshima bombs. 7,000 nuclear detonations compressed into the motion of one small spacecraft. That is the energy price for the cheapest possible interstellar ticket. Not for a crewed vessel, not for a round trip, just a tiny robot aimed at the closest star with no ability to stop. And we have not yet considered stopping. A probe that arrives at Alpha Centauri at 10% of light speed will fly past the entire star system in a matter of hours unless it slows down. Slowing down requires the same energy as speeding up, applied in reverse. The energy budget just doubled. 14,000 Hiroshima bombs worth of energy for a car-sized robot to visit the nearest star and actually come to rest when it arrives. This is the scale of the problem for the simplest conceivable interstellar mission. A mission with no passengers, no return journey, and a destination only 4 light years away. Here is a fact that sits at the heart of modern physics and cannot be wished away. The energy required to accelerate any mass to any speed is not a human equation. It is a universal equation. It applies to every civilization everywhere. A species 10,000 years more advanced than us must still obey the same relationship between mass, velocity, and kinetic energy. They can build more efficient engines. They can harness more total power. But they cannot reduce the minimum energy the trip demands. That minimum is set by physics, not by engineering. Consider a simple comparison. Lifting a 1 kilogram object 1 meter against Earth's gravity requires about 10 joules of energy. This is true whether you lift it with your hand, a machine, or a robot built by the most advanced civilization imaginable. The method changes. The energy does not. You can waste less energy on friction and heat. You can approach perfect efficiency, but you cannot spend less than 10 joules because gravity sets that floor. The universe sets the price. For technology only determines how close you get to paying that exact price and not a joule more. The same principle governs interstellar propulsion. The minimum energy to accelerate 1,000 kilograms to 10% of light speed is fixed. No technology reduces it. No breakthrough lowers it. No alien genius negotiates a discount. The floor is set by the mass, the velocity, and the speed of light. These are constants of the universe, and not features of any particular species' engineering. Some physicists have speculated, somewhat controversially, that energy cost may function as a kind of universal filter. Not a great filter in the traditional sense, but something quieter. A passive economic barrier that makes interstellar travel so expensive that even civilizations capable of attempting it choose not to. The cost-benefit analysis simply never works out. The energy spent on one interstellar mission could power an entire civilization for years. The return on investment is uncertain at best and non-existent at worst. This idea remains debated. But the math behind it is not. Everything gets worse from here, because we have only talked about the raw energy so far. We have not yet talked about the fuel needed to generate that energy. And the fuel problem does not just add to the difficulty. It multiplies it in ways that border on mathematical cruelty. The energy wall is enormous, but energy alone does not tell the full story. Because energy must come from somewhere. It must be stored in something. It must be carried aboard the ship. And the moment you start carrying fuel, you step into a trap that has haunted rocket science since its very beginning. A trap so elegant and so merciless that it has its own name. The tyranny of the rocket equation. The equation itself was first published by a Russian scientist named Konstantin Tsiolkovsky in 1903. It describes a simple but brutal relationship. To go faster, you need more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that extra weight, which adds more mass, which requires more fuel. The cycle feeds on itself like a fire that grows by eating its own oxygen. The fuel requirements do not grow steadily with speed. They grow exponentially. Each doubling of velocity does not double the fuel. It squares it, or worse. The curve rises so steeply that at a certain point it stops being an engineering problem and becomes a mathematical impossibility. For chemical rockets, the kind that have carried every human mission from the first satellites to the moon landings, the situation is hopeless from the start. Chemical rockets produce exhaust velocities of roughly 4.5 kilometers per second. This is fast enough to reach orbit, fast enough to send probes to other planets within our solar system. But reaching even 1% of light speed with chemical propulsion would require a fuel-to-payload ratio so extreme that the spacecraft would need to be almost entirely fuel. There would be no room for instruments, no room for structure, so no room for anything except the fuel needed to burn more fuel. And reaching 10% of light speed with chemical rockets is not impractical. It is mathematically impossible. The amount of fuel required exceeds the mass of the observable universe. This is not an exaggeration designed to impress you. It is a direct result of the exponential function growing that aggressively against exhaust velocities that low. Nuclear propulsion offers an improvement, but does not escape the fundamental trap. A nuclear thermal rocket heats propellant using a fission reactor and achieves exhaust velocities roughly twice those of chemical rockets. Better, but still nowhere near enough. Nuclear pulse propulsion, a concept explored in the theoretical Project Orion during the 1950s, proposed an even more dramatic approach. Detonate nuclear bombs behind the spacecraft and ride the shockwaves. The designers estimated that Orion could reach perhaps 3 to 5% of light speed. This was a concept that required detonating thousands of nuclear warheads in sequence behind a spacecraft the size of a city, carrying a stockpile of weapons that would dwarf every Cold War arsenal combined. And even this extraordinary, violent, almost absurd concept could not approach the velocities needed for practical interstellar travel. The rocket equation consumed its advantages just as it consumed the advantages of every chemical engine before it. Fusion propulsion represents what many physicists consider the most promising option beyond nuclear pulse concepts. Fusion releases roughly 4 times more energy per kilogram of fuel than fission. Hydrogen, the fuel for fusion, is the most abundant element in the universe. A working fusion drive could theoretically achieve exhaust velocities of several percent of light speed, bringing interstellar missions into the realm of centuries rather than millennia. On paper, fusion looks like the answer. In practice, it remains beyond our reach, despite more than 70 years of dedicated effort and hundreds of billions of dollars in global investment. The core challenge is containment. Fusion requires heating hydrogen isotopes to temperatures exceeding 100 million degrees Celsius. That is roughly 6 times hotter than the core of the Sun. At these temperatures, matter becomes plasma, a state so energetic that it destroys any physical container it touches. Current approaches use powerful magnetic fields to suspend the plasma in a vacuum, preventing it from melting through the reactor walls. This magnetic confinement must be sustained continuously with extraordinary precision, while the plasma twists and writhes in chaotic turbulence. Every time engineers solve one instability, another appears. Every time they extend confinement for a few more seconds, new energy loss mechanisms emerge. The plasma does not cooperate. It finds every weakness in the magnetic bottle and exploits it. The history of fusion research is a long story of promises pushed into the future. In the 1950s, scientists said 20 years. In the 1970s, they said 30 years. In the 2000s, they said 30 years again. The joke among plasma physicists is that fusion is always 30 years away. This is not because the scientists are foolish. It is because the physics is genuinely, stubbornly, almost cruelly difficult. As of today, no fusion reactor on Earth has produced more energy than it consumed in a sustained and repeatable way. The International Thermonuclear Experimental Reactor, known as ITER, is the most ambitious fusion experiment ever attempted. Its construction has taken decades. Its budget has swelled to roughly $25 billion. If it succeeds, ITER will produce approximately 500 megawatts of fusion power for periods of minutes. 500 megawatts for minutes. The energy needed to accelerate even a small interstellar probe requires power outputs millions of times greater, sustained not for minutes, but for months or years of continuous thrust. The gap between where fusion research stands today and where it would need to stand for interstellar propulsion is not a gap the next generation will close. It is a chasm spanning multiple fundamental breakthroughs, each of which may or may not prove achievable. Here is a fact that carries real weight in this discussion. The rocket equation applies to every civilization in the universe that carries its own fuel. It is not a human limitation. It is a mathematical truth. Any alien species building a rocket that stores propellant on board must face the same exponential relationship between speed and fuel mass. Their chemistry might be different, their engineering might be superior, but the equation does not care about chemistry or engineering. It cares about the ratio of exhaust velocity to desired velocity, and that ratio determines whether the mission is possible or absurd. There is also a speculative idea worth mentioning here, because it reveals how deep this problem goes. Some theorists have proposed that the rocket equation might function as a kind of cosmic filter, quietly preventing civilizations from spreading beyond their home star systems, not through any dramatic catastrophe, but through simple economics. The fuel cost of interstellar travel is so extreme that any civilization performing an honest cost-benefit analysis would conclude that the resources are better spent at home, improving their own world, exploring their own solar system, building orbital habitats around their own star. The stars beyond remain beautiful but unreachable, not because of any single barrier, but because the exponential mathematics of rocketry make the price too high and the payoff too uncertain. This is the trap, not a wall you hit once, but a loop you cannot escape. More speed demands more fuel demands more mass demands more speed. The circle tightens with every turn, and no engine yet conceived, chemical, nuclear, or fusion, has found a way to break free. But there is one fuel source that stands above all others, one theoretical option that converts mass into energy with perfect efficiency. It is the ultimate fuel, the ceiling of physics itself. And even it is not enough. There is one fuel that sits at the absolute top of physics, one substance that converts mass into energy with perfect total efficiency. Nothing wasted, nothing left behind, every atom transformed entirely into pure power. It is called antimatter, and it is the most energy-dense material that the laws of physics allow to exist. When matter meets antimatter, they annihilate each other completely. Every particle and its antiparticle vanish together, and their combined mass converts entirely into energy, according to Einstein's famous equation. Energy equals mass times the speed of light squared. No other reaction in all of physics achieves this efficiency. Chemical combustion, the kind that powers every car engine and every campfire, converts less than 1/10,000,000% of fuel mass into energy. Nuclear fission, the reaction inside atomic bombs and power plants, converts roughly 0.1%. Nuclear fusion, The reaction that powers the sun converts roughly 0.7%. Antimatter annihilation converts 100%. It is the ceiling, the theoretical maximum, the best the universe allows. If any fuel could make interstellar travel practical, antimatter would be the one. And yet, even antimatter is not enough to make the journey easy. It merely shifts the problem from impossible to extraordinarily, almost absurdly difficult. To accelerate a small 1,000 kilogram probe to 10% of light speed using antimatter propulsion, you would need approximately 500 kilograms of antimatter combined with 500 kilograms of normal matter. 1,000 kilograms of total fuel for 1,000 kilograms of payload. A 1-to-1 ratio. Compared to the nightmare ratios demanded by chemical or nuclear rockets, this sounds almost reasonable, almost manageable. So until you learn how much antimatter humanity has actually produced. The total amount of antimatter created by every particle accelerator on Earth across the entire history of physics amounts to roughly 20 nanograms. A nanogram is 1/1,000,000th of a gram. 20 nanograms would not be visible to your naked eye. It would not register on a kitchen scale. It would barely register on most laboratory scales. If you collected every single atom of antimatter that every accelerator in every country has ever produced across every decade of particle physics research, the resulting speck would sit on the tip of a needle and disappear from sight. The gap between 20 nanograms and 500 kilograms is not a gap that the word gap can honestly describe. 500 kilograms is 500 trillion times more than what we have ever produced. 500 trillion. The number itself resists comprehension. It is like standing at the edge of a puddle and being told you need to fill an ocean. The cost of producing antimatter makes the quantity problem even more devastating. Manufacturing a single gram of antimatter using current technology would require approximately $25 trillion and roughly 25 million billion watt-hours of energy. $25 trillion exceeds the entire gross domestic product of the United States. The energy required exceeds the annual output of thousands of power plants, and that is for 1 gram. A mass you could hold on your fingertip without feeling its weight. Producing 500 kilograms would require the entire global economy, every dollar earned by every person in every country, redirected entirely toward antimatter production, operating for millions of years. The timeline is not centuries, it is not millennia. It is millions of years of total civilizational effort for the fuel needed to send a single car-sized probe to the nearest star. Now scale upward. A car-sized probe is the simplest possible mission. No crew, no life support, no return trip. If you want to send actual living beings between stars, the spacecraft must carry people along with everything needed to keep them alive. Air recycling systems, water purification, food production or storage, radiation shielding, medical equipment, navigation systems, communication systems, structural materials strong enough to hold it all together across decades of flight. Such a vessel would mass at absolute minimum hundreds of thousands of kilograms. Realistic estimates for a crewed interstellar craft range from 1 million to 100 million kilograms. The antimatter fuel requirements scale directly with the mass. A 100 million kilogram spacecraft would need roughly 50 million kilograms of antimatter. Producing this quantity would require energy inputs so vast they exceed the total energy output of current human civilization by many orders of magnitude. The numbers do not merely stretch belief, they leave the territory of meaningful discussion entirely and drift into pure mathematical abstraction, or numbers you can write on paper but cannot connect to any physical reality you have ever experienced. Here is a scientific fact that makes this even more sobering. Antimatter is not just hard to produce, it is extraordinarily hard to store. Antimatter annihilates on contact with any normal matter. You cannot put it in a bottle. You cannot keep it in a tank. The moment it touches the walls of its container, both the antimatter and the wall destroy each other in a burst of energy. Current storage methods use magnetic traps called penning traps that suspend tiny amounts of antimatter in a vacuum using electromagnetic fields. These traps can hold individual atoms of antihydrogen for minutes or hours. Storing kilograms of antimatter for years or decades aboard a spacecraft traveling through the vibrations and stresses of interstellar flight is a challenge so far beyond current capability that no serious timeline can be placed on it. And here is something that lives on the speculative edge of this discussion. Some physicists have wondered whether there might exist natural sources of antimatter somewhere in the universe, regions where antimatter accumulated during the early moments after the Big Bang, or processes that produce antimatter in quantities larger than our particle accelerators can manage. If such sources existed and could somehow be harvested, the production problem might shrink, but no such sources have ever been observed. Every observation of the cosmos suggests that the universe is overwhelmingly dominated by normal matter. The apparent absence of large-scale antimatter in the observable universe is itself one of the great unsolved mysteries of physics, known as the baryon asymmetry problem. Why the universe contains so much matter and so little antimatter remains an open question, debated actively by cosmologists and particle physicists. But for the practical question of interstellar travel, the answer is clear. There is no shortcut to cheap antimatter. The universe did not leave fuel depots scattered conveniently between the stars. This is the ceiling of physics. Antimatter represents the maximum energy any fuel can provide per kilogram. And even at maximum efficiency, the quantities required for interstellar travel are so enormous, the production costs so extreme, and the storage challenges so far beyond current science that the fuel problem remains effectively unsolvable. Not unsolvable in the way that a difficult puzzle is unsolvable before someone finds the trick. Unsolvable in the way that a wall is unsolvable when it is built from the fundamental constants of the universe itself. Every fuel source tells the same story. Chemical rockets cannot reach the needed speeds. Nuclear rockets improve the numbers, but cannot escape the equation. Fusion remains unachieved after 70 years of trying. And antimatter, the ultimate theoretical fuel, it exists in quantities so small and costs so much to produce that it might as well be imaginary. The universe has placed a price tag on interstellar travel, and every currency we know, every fuel we can imagine, falls short of paying it. But there is one idea that attempts to sidestep the fuel problem entirely. One concept that says, forget carrying fuel, leave the energy source at home and push the ship from behind. It sounds like a solution. It is not. Every propulsion method we have explored so far carries the same curse. The fuel travels with the ship, and because the fuel has mass, it must itself be accelerated, which demands more fuel, which adds more mass, which demands still more fuel. The rocket equation tightens its grip with every kilogram added to the load. But what if you could leave the fuel behind entirely? What if the energy source stayed at home and the ship carried nothing but a sail to catch the push? This is the idea behind laser propulsion, sometimes called a light sail or beam-powered propulsion. The concept is beautifully simple. A spacecraft carries an enormous but extremely lightweight reflective sail. A ground-based or space-based laser array fires a concentrated beam of light at that sail. Photons from the laser bounce off the reflective surface, transferring their momentum and gradually pushing the craft faster and faster. No onboard fuel, no exhaust, no rocket equation. the energy source remains safely behind while the ship glides outward on a beam of pure light. It sounds like the answer to everything we have discussed. It eliminates the tyranny of fuel mass entirely. For the first time in this story, the math seems like it might actually close. It does not. In 2016, a project called Breakthrough Starshot was announced with great excitement. Backed by significant funding and serious scientific minds, it proposed using exactly this approach. The plan was elegant in its ambition. Build a ground-based laser array with a total power output of approximately 100 gigawatts. That is roughly the total electrical generating capacity of a medium-sized industrialized country like the United Kingdom. Aim this entire national energy output as a coherent laser beam at a tiny reflective sail smaller than a bedsheet. Attached to that sail would be a probe weighing roughly 1 gram, a chip-sized sensor package lighter than a paperclip. The laser would fire for roughly 10 minutes, accelerating this gram-scale probe to 20% of light speed. At that velocity, the probe would reach Alpha Centauri in approximately 20 years. 1 gram, the mass of a small paperclip. And reaching the nearest star with that paperclip requires focusing the entire electrical output of a nation into a beam of light for 10 minutes. Not a large spacecraft. Not a useful robotic explorer by most standards. A chip, a tiny sensor package that might carry a simple camera and a basic communication system. That is what 100 gigawatts buys you. 1 gram to 1 star in 20 years. Now try to scale this up. A probe weighing just 10 kilograms, something large enough to carry a decent camera, a communication antenna, and maybe a few scientific instruments, would require laser arrays producing tens of thousands of gigawatts, more energy than the entire human civilization currently produces. A probe weighing 1,000 kilograms, our familiar car-sized benchmark, would demand power outputs so far beyond any existing or planned infrastructure that the numbers become essentially fictional. The light sail eliminates the rocket equation, but it replaces it with an energy generation problem of almost equal impossibility. And there is a deeper flaw built into this concept that no amount of power can fix. The laser can only push. It cannot pull. A light sail accelerated to 20% of light speed has absolutely no way to slow down when it reaches its destination. It screams past the target star system in a matter of hours, perhaps snapping a few blurry photographs as the stars and planets smear past in a flash. Then it vanishes into the interstellar void beyond, still moving at 20% of light speed, with no way to stop, no way to turn around, and no destination ahead. It becomes another piece of cosmic debris, a gram-scale artifact tumbling through darkness forever. To slow down at the destination, you would need a second laser array already waiting there. Positioned in the target star system, aimed back at the incoming sail, firing with enough power to decelerate it from 20% of light speed to a gentle stop. But building a laser array at Alpha Centauri means someone must have already traveled there to construct it, which means you have not solved the problem of interstellar travel. You have merely assumed the solution already exists at the other end. The logic eats itself. Some creative proposals have suggested using the target star's own light to decelerate. The idea is to flip the sail around as the ship approaches, letting the star's radiation pressure push against it like a brake. In principle, this works. In practice, it fails. A sail arriving at 20% of light speed carries enormous kinetic energy. Stellar light pressure is far too weak to absorb that energy in the brief window before the craft overshoots the system entirely. To make stellar braking work, the sail would need to be impractically gigantic stretching thousands of kilometers across. And even then, the deceleration would take years, during which the craft overshoots its target by trillions of miles and must somehow loop back. The physics simply does not close. The numbers refuse to cooperate. Here is a well-established scientific fact that adds another layer of difficulty. At 20% of light speed, the sparse hydrogen atoms drifting through interstellar space stop being harmless background particles. They become tiny bullets. Each hydrogen atom strikes the front of the sail with energy in the megaelectron volt range. Over a journey of several light years, the cumulative bombardment would erode the sail material at the molecular level. A sail thin enough to be pushed effectively by a laser is also thin enough to be gradually destroyed by the interstellar medium it flies through. The very property that makes the sail work, its extreme thinness and lightness, also makes it vulnerable to the environment it must survive. Engineers working on breakthrough Starshot have acknowledged this problem openly. Proposed solutions include special coatings and self-healing materials, but at 20% of light speed, the energies involved push far beyond what any existing material science can comfortably handle. And here is something speculative that deserves a quiet moment of thought. Some researchers have wondered whether laser propulsion might be more useful as a signaling tool than a transportation method. Instead of pushing ships, perhaps advanced civilizations use powerful laser arrays to send focused beams of information across interstellar distances. Light carries data far more efficiently than it carries mass. A civilization that abandons the dream of physical travel might instead build vast laser communication networks, sending knowledge, culture, and consciousness itself as encoded light between the stars. The ship never arrives, but the message does. This idea lives on the fringe of serious astrobiology discussions, but it carries a strange elegance. Perhaps the universe does not forbid connection between civilizations. Perhaps it only forbids physical visitation. The door is locked, but the window might be cracked open just enough for a whisper to pass through. There is also an open scientific debate about whether laser propulsion might work better at much lower speeds. Instead of pushing a tiny probe to 20% of light speed, perhaps a larger, more useful spacecraft could be accelerated to just 1 or 2% of light speed. The energy requirements drop significantly. The interstellar erosion problem eases. The journey time to Alpha Centauri stretches from 20 years to several centuries, but the mission becomes more scientifically valuable because the probe can carry real instruments and possibly even decelerate using a combination of stellar braking and onboard propulsion. This slower approach trades speed for practicality. But centuries-long missions introduce their own category of problems that we have not yet fully explored. Because every propulsion method we have examined, from chemical rockets to antimatter engines to laser sails, are eventually runs into the same silent enemy. Not distance, not energy, something more patient, something that cannot be outrun or outbuilt or outsmarted, something that simply passes moment by moment, year by year, wearing down everything it touches with perfect, unhurried indifference. The enemy is time, and time is where the story takes its cruelest turn. Every barrier we have traced so far sits on a balance sheet. Distance can be measured in miles, energy can be calculated in joules, fuel mass can be weighed in kilograms. These are enormous numbers, crushing numbers, numbers that break every analogy we reach for. But they are at least static. They sit still on a page and wait to be evaluated. The barrier we enter now does not sit still. It moves. It passes. It erodes everything it touches with a patience so absolute that no engineering can match it. The barrier is time. And time is the cruelest constraint of all. not because it is the largest, but because it attacks everything simultaneously. The ship, the crew, the civilization behind them. The very purpose that made the journey seem worth attempting in the first place. Begin with a simple, concrete example. 10% of light speed is an ambitious but theoretically conceivable velocity. We established that getting there demands energy equivalent to thousands of nuclear detonations. But suppose the fuel problem is somehow solved. The ship accelerates. It reaches 67 million miles per hour. The star behind it shrinks to a point. The journey has begun. And at this extraordinary velocity, the trip to Alpha Centauri, the closest star system to our Sun, takes 42 years. One way, not round trip, just getting there. A crew member who boards the ship at the age of 30 arrives at the destination at age 72. Assuming the ship performs flawlessly for over 4 decades. Assuming the human body survives decades in deep space without catastrophic breakdown. Assuming nothing unexpected happens in 42 years of continuous flight through the interstellar void. The return trip doubles the timeline to 84 years. A full mission to the nearest star and back would consume an entire human lifetime. The person who steps onto the ship is not the same person who steps off. They have aged beyond recognition. Everyone they left behind has aged alongside them or died. The world they departed has changed in ways they could not predict. They return as strangers, and Alpha Centauri is the best case, the closest star, the galaxy's front door. We scale the math to anything deeper, and the numbers stop being human. At 10% of light speed, a journey to a star 100 light-years away takes 1,000 years. A star 500 light-years away takes 5,000 years. A star 1,000 light-years distant takes 10,000 years. 10,000 years ago, human beings had not yet invented writing. They had not built cities. They had not domesticated horses or planted their first fields. The entire arc of recorded human civilization, every book, every empire, every scientific discovery, every war and every peace treaty fits inside the travel time for a single interstellar journey at 10% of light speed to a moderately distant star. Now, reduce the speed to something more realistic for a large crewed vessel. Accounting for fuel mass, structural constraints, and engineering realities, a practical large spacecraft might achieve 1% of light speed. At roughly 6.7 million miles per hour, this sounds impressive. But the nearest star now requires 424 years. A star 100 light-years away takes 10,000 years. These are not travel times that any individual can survive. They are not times that any crew can endure. They are durations that exceed the lifespan of every empire, every religion, every language, and every cultural tradition that humanity has ever produced. Here is where time dilation enters the conversation. Special relativity tells us that time does not pass at the same rate for everyone. An object moving at high speed experiences time more slowly than an observer who remains still. This is not a theory. It has been confirmed by atomic clocks on aircraft, by the behavior of unstable particles in accelerators, and by the corrections built into GPS satellites to account for relativistic effects. It is one of the most tested facts in all of physics. At 90% of light speed, a crew would experience time passing at roughly 44% of the rate felt by people on their homeworld. At 99% of light speed, they would experience only about 14 years for every 100 years that pass at home. This sounds like a solution. If time slows down for fast-moving travelers, they could survive much longer journeys. And in a narrow technical sense, this is true. A crew traveling at 99% of light speed to a star 100 light-years away would experience only about 14 years of subjective time. they would arrive biologically young, still capable of exploring their destination. But here is what time dilation does not fix. While 14 years pass for the crew, 100 years pass at home. Every person they knew when they departed is dead. The civilization they left behind has had a full century to transform, forget them, change its values, change its technology, change its very definition of why the mission mattered. The crew steps off the ship into a future that did not wait for them. They are not just travelers in space, they are travelers in time. And the journey forward through time is one way only. And reaching 99% of light speed brings us crashing back into the energy wall. The relativistic mass increase at this velocity means the energy required for acceleration is not doubled or tripled compared to lower speeds. It is multiplied by a factor of roughly 7. The fuel requirements, the engineering tolerances, the shielding demands, everything escalates by nearly an order of magnitude above what was already effectively impossible. Time dilation does not come free. It is purchased at a cost that makes even our earlier staggering numbers look modest. There is something else that the clock measures, something less obvious but equally devastating. Communication. Information traveling between the ship and its homeworld can move no faster than light. This means that for every light year of distance the ship covers, messages home take 1 year to arrive, replies take another year to return. By the time the ship has traveled just 10 light years from home, a single exchange of information takes more than 20 years. A practical conversation has become impossible. Within a few decades of departure, the crew is functionally alone. Not just isolated in space, isolated in time. Living in a present that the home civilization cannot share, cannot guide, cannot respond to in any meaningful way. Imagine the ship encounters a critical problem 50 years into the journey. The crew sends an urgent message home. 50 years later, that message arrives at a civilization that has changed almost beyond recognition. The engineers who designed the ship may be dead. The institutions that funded the mission may no longer exist. The people who receive the message must piece together the context of a 50-year-old emergency and formulate a response. Their reply travels 50 years back. By the time it arrives, a century has passed since the problem was first reported. The crew who sent the distress call are old or gone. Their children or grandchildren inherit an answer written for a situation that no longer exists in the same form. This is not a communication delay. This is a complete breakdown of the very concept of connected mission control. A current open debate in the field of astrobiology and the search for extraterrestrial intelligence touches on this exact problem. If other civilizations have faced these same time barriers, perhaps they abandoned physical travel entirely in favor of something else. Perhaps they uploaded their minds into digital form and transmitted themselves as encoded information at light speed. Perhaps they built self-replicating machines to explore on their behalf. Perhaps they simply looked at the math, accepted the isolation, and turned their attention inward. No one knows. The debate remains genuinely open. But the fact that it exists, the fact that serious scientists discuss abandoning physical interstellar travel as a rational response to the time problem, tells you something important about how deep this barrier runs. Time does not fight you. It does not resist you. It simply passes. And in passing, it quietly dismantles every structure, every plan, every civilization, and every dream that was not built to last forever. Nothing has ever been built to last forever, and the stars are very far away. Time, as we have just felt it, is already devastating enough when applied to a single crew making a single journey. But the journeys required to reach most stars in the Milky Way are not measured in decades. They are measured in centuries and millennia. No individual can survive that long. No small crew can endure it. So a different idea emerges from the wreckage of simpler proposals. An idea that attempts to solve the time problem not by speeding up the ship, but by changing who is aboard it. The idea is called a generation ship, and on the surface, it sounds like a solution. Beneath the surface, it is a catalogue of cascading failures waiting to unfold across thousands of years. The concept is straightforward. Build a vessel large enough to house not just a crew, but an entire self-sustaining community. A population that lives, reproduces, and dies aboard the ship across multiple generations. The original travelers never expect to arrive. Their children do not expect to arrive. Their grandchildren do not either. Generation after generation is born inside the ship, lives their entire life inside the ship, and passes the mission forward to the next generation like a relay baton, handed through the centuries. The final generation, born thousands of years after the launch, steps off onto the destination world that their distant ancestors chose from a planet they can now barely imagine. It is an elegant idea in the abstract. In practice, it begins to break apart almost immediately when you push on the details. Start with biology. A generation ship is a closed system. Nothing comes in from outside. No new genetic material, no new people, no new organisms. Whatever leaves the homeworld is all there ever is. Genetic science tells us that a population confined to a small closed group faces serious risks over many generations. Inbreeding depression, the harmful effects of closely related individuals reproducing together, reduces fertility, increases the frequency of genetic diseases, and weakens the immune system. To avoid these effects across thousands of years and hundreds of generations, geneticists estimate that the minimum viable population for a long-duration closed community is somewhere between 5,000 and 10,000 individuals. Some estimates place it even higher when accounting for the full length of a generational voyage and the need to maintain enough genetic diversity to adapt to an entirely new planetary environment upon arrival. 10,000 people is not a skeleton crew of brave volunteers. It is a small city, housing, feeding, clothing, educating, and sustaining 10,000 human beings in a sealed metal container hurtling through a vacuum at millions of miles per hour, requires a vessel of truly enormous size and complexity. The mass of such a ship pushes the energy requirements for acceleration into numbers that make even our earlier impossible figures look conservative. The fuel problem, which already seemed insurmountable for a small probe, now grows by orders of magnitude. But population size is only the beginning. A closed ecological system must recycle every molecule perfectly. Water must be purified and redistributed indefinitely. Air must be scrubbed of carbon dioxide and replenished with oxygen continuously. Food must be grown, harvested, processed, and consumed in an endless cycle with no external inputs. Waste must be broken down and reintegrated into the biological loop without accumulation of toxins or loss of essential nutrients. Every molecule that enters one process must emerge from another in a form that the system can use again. No closed ecological system has ever been sustained by humans for more than a few years. Biosphere 2, the most ambitious attempt ever made, sealed 8 people inside a carefully designed 3-acre enclosed environment in Arizona in 1991. Within 2 years, oxygen levels had dropped dangerously, crop yields had fallen, species within the ecosystem had gone extinct, and the entire experiment required external intervention to prevent collapse. 8 people, 3 acres, 2 years, on the surface of Earth, with gravity, natural light cycles, and the ability to call for help. A generation ship must sustain thousands of people in a sealed metal structure in deep space for thousands of years. With no sunlight, no natural gravity, no outside assistance, and zero tolerance for critical system failure. The social dimension compounds the biological one with equal severity. Human societies are not stable across millennia. History makes this abundantly clear. Every civilization ever recorded has eventually fragmented, transformed, or collapsed. Languages change beyond recognition within a few centuries. Values shift, power structures reorganize. Religious movements rise and remake entire cultures within a single lifetime. Over thousands of years aboard a confined vessel, with no outside contact, no immigration, and no horizon beyond the same familiar walls, the social pressures would be extraordinary. Consider what the ship looks like 500 years into a 10,000-year voyage. 20 generations have lived and died aboard it. The original crew are mythological figures, names in a database, faces in old photographs that fewer and fewer people stop to look at. No one alive has ever seen a sky. No one has ever felt wind or rain or stood beside an ocean. The mission was conceived by people so distant in time that their language has drifted, their cultural references have faded, and their reasons for launching have been reinterpreted dozens of times through the lens of each new generation's experience. Some people aboard believe the mission is sacred, a holy obligation inherited from ancestors who saw a truth the present generation must honor. Others believe it is a prison sentence imposed by long-dead individuals who had no right to condemn their descendants to life inside a metal tube with no choice in the matter. A third faction has developed a belief system that reframes the ship itself as the only true world, teaching that the idea of a home planet is mythology and that the concept of a destination is a dangerous fantasy. These factions do not simply disagree. They compete for resources, for control of governance systems, for influence over what the next generation is taught about why they exist and where they are going. Some conflicts are resolved through negotiation, others are not. Over 10,000 years, violence is not merely possible, it is statistically inevitable. Mechanical degradation runs parallel to social collapse. Every material in existence degrades over time. Metals fatigue under repeated stress cycles. Seals and gaskets erode. Electronics fail as radiation displaces atoms within their circuits. Lubricants break down. Structural components crack under thermal cycling. A generation ship must maintain every critical system: propulsion, navigation, life support, power generation, radiation shielding, and hull integrity across timescales that dwarf the operational lifespan of any machine humanity has ever built. The longest operating human-made machines have lasted perhaps a few centuries under favorable conditions on Earth's surface. A generation ship must operate in hard vacuum, bombarded by cosmic radiation for thousands of years without resupply or external maintenance. Here is a fact from reliability engineering that crystallizes the problem. A system with a 99.9% annual survival probability, meaning just one chance in 1,000 of catastrophic failure in any given year, has only a tiny fraction of a percent chance of surviving 10,000 years without a single failure. To achieve even a 50% chance of lasting 10,000 years, every critical system must have an annual failure probability of less than 1 in 144,000. These are reliability levels that no human technology has ever approached, sustained not for one system, but for thousands of interdependent systems operating simultaneously in the most hostile environment known to exist. There is also an open scientific debate about whether a generation ship population would even want to arrive. Researchers in the emerging field of closed environment psychology have noted that populations adapted to life inside a bounded, predictable structure over many generations might develop a deep psychological resistance to the idea of leaving it. The ship becomes not a vehicle, but a world. The destination becomes not a home, but a threat, an alien environment of open sky, unknown weather, strange gravity, and unfamiliar biology might be experienced not as liberation, but as terror. The very success of the biological mission, a population that has thrived inside the ship for millennia, it might produce a community that actively refuses to disembark. Every proposed solution to the generation ship problem introduces new problems equally difficult. Every answer opens a new question. Every door leads to another wall. And all of this assumes the ship was launched in the first place, which requires solving the energy problem, the fuel problem, and the propulsion problem that we have already seen are themselves effectively unsolvable. The generation ship is not a backup plan. It is a dream built on foundations that cannot hold the weight of the mathematics placed upon them. Every barrier explored in this journey so far invites the same rebuttal. It arrives reliably, with a confidence that feels like wisdom, but carries a hidden flaw. The rebuttal sounds like this: you are thinking too small. You are projecting human limitations onto beings who may have existed for millions of years longer than us. A civilization that ancient, that intelligent, that far beyond anything we can currently conceive, would simply find a way around these barriers. They always find a way. Give intelligence enough time and no wall stands forever. This argument feels humble. It feels open-minded. It feels like the kind of generous thinking that serious people should embrace when contemplating the vastness of cosmic possibility. But it contains a flaw so fundamental that it undermines everything built upon it. The barriers described throughout this journey are not human limitations. They are not artifacts of our early-stage technology or our incomplete understanding. They are properties of the universe itself, and the universe does not grant exemptions based on intelligence, age, or ambition. Begin with the most structured version of this argument. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations by their total energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the power of 16 watts for an Earth-sized world. A Type 2 civilization captures the entire energy output of its host star, roughly 4 times 10 to the power of 26 watts for a Sun-like star. A Type 3 civilization commands the energy output of its entire galaxy, roughly 4 times 10 to the power of 36 watts. Humanity currently sits at approximately 0.7 on this scale. We have not yet captured all the energy reaching Earth from the Sun, let alone the Sun's total output. The Kardashev scale is frequently invoked to suggest that sufficiently advanced civilizations would find interstellar travel trivially affordable. A Type 2 civilization commanding the full power of a star should launch starships the way we launch weather satellites. A Type 3 civilization harnessing an entire galaxy should scatter probes across the cosmos like seeds thrown into wind. The energy wall would crumble before such staggering power. See, so the argument goes. But this reasoning makes a critical mistake. It confuses the total energy available with the energy required for a specific physical task. A Type 2 civilization has access to enormous power. That is not in question. What is in question is whether all that power changes the physics of the journey itself. And the answer is no. The minimum kinetic energy needed to accelerate a given mass to a given velocity is fixed by the relationship between mass, see velocity, and the speed of light. These are constants. They do not shift based on who is doing the engineering. More available power means the civilization can afford the bill more comfortably. It does not make the bill smaller. The universe sets the price. Technology only determines how efficiently you pay it. Consider the analogy. Lifting a 1 kilogram object 1 meter against Earth's gravity requires 10 joules. This is true regardless of whether you lift it by hand, or by pulley, or using a robotic arm designed by the most sophisticated engineers in history. The mechanism changes, the energy requirement does not. You can approach perfect efficiency and waste nothing, but you cannot spend less than 10 joules because gravity sets that floor. The same principle applies to interstellar propulsion. No civilization, regardless of its advancement, pays less than the minimum kinetic energy demanded by the mass and the velocity. The floor is set by physics, not by engineering. Now, address the proposals that claim to bypass physics entirely rather than simply overpowering it. Warp drives, wormholes, faster than light travel. These concepts appear so regularly in science fiction that many people assume they represent genuine possibilities, awaiting only sufficient technological advancement to unlock. They do not. The warp drive concept was given a mathematical framework by physicist Miguel Alcubierre in 1994. His proposal involves contracting space in front of a vessel and expanding it behind, creating a bubble of warped spacetime that carries the ship faster than light without the ship itself exceeding light speed within its local space. The mathematics are internally consistent within general relativity. The physics, however, are entirely devastating. An Alcubierre drive requires exotic matter with negative energy density to sustain the warp bubble. Negative energy density means matter that weighs less than nothing, that repels gravity rather than attracting it. No such material has ever been observed anywhere in the universe. No theoretical framework produces it in usable quantities. Early calculations of the energy required to create and sustain a warp bubble placed the number at greater than the mass energy of the entire observable universe. Later, mathematical refinements reduced this estimate significantly, but even the most optimistic figures require conditions, materials, and energy states that have never been observed in nature at any scale. Calling the warp drive speculative is generous. It is a mathematical curiosity, not an engineering blueprint. Wormholes face identical objections. A wormhole is a theoretical tunnel through spacetime connecting two distant points. If stable, traversable wormholes could be created and maintained, they would allow something close to instant travel between vastly separated locations. But every known solution to the equations of general relativity that produces a wormhole also requires the same exotic matter with negative energy density to hold it open. Without this material, the wormhole collapses faster than any object could pass through it, and traversable wormholes would likely violate causality, the principle that causes always precede their effects. If you can travel instantly between distant points, then through a straightforward application of special relativity, you can arrive at your destination before you departed. This creates time travel paradoxes that most physicists consider strong evidence that traversable wormholes simply cannot exist. The universe appears to enforce what Stephen Hawking called the chronology protection conjecture, an unproven but widely suspected principle that the laws of physics conspire to prevent time travel. Faster than light travel of any kind collides with the same structural barrier. Special relativity does not merely say that nothing currently exceeds light speed. It says that the structure of spacetime forbids it for anything with mass. As any massive object approaches light speed, the energy required to accelerate it further approaches mathematical infinity. Not a very large finite number. Actual infinity. You cannot reach infinity. You cannot engineer around it. The speed of light is not a wall you can blast through with a bigger engine. It is the geometry of the room itself. You cannot break the walls of a room that you are made of. These are not provisional ideas waiting to be overturned by the next generation of discoveries. A special relativity has been confirmed by every experiment ever designed to test it across more than a century of increasingly precise measurements. Its predictions have been verified in particle accelerators, in astronomical observations, in GPS satellites, and in gravitational wave detectors. The speed of light as an absolute limit is among the most firmly established facts in all of human science. There is also a temporal dimension the advanced civilization argument consistently ignores. Civilizations do not last forever. They rise, flourish, and decline with a regularity that every page of history confirms. The window during which a civilization possesses both the technology to attempt interstellar travel and the institutional stability to actually execute such missions may be remarkably narrow. A few centuries, perhaps a few millennia at most. Interstellar travel at achievable velocities demands mission durations of thousands to tens of thousands of years. The mission must outlast the civilization that launched it, not by a small margin, but by orders of magnitude. Here is an open debate that sits at the heart of the Fermi paradox. If advanced civilizations do reach Type 2 or Type 3 status, do they inevitably turn inward rather than outward? Some researchers argue that a civilization with unlimited stellar energy would find far more value in simulating vast virtual realities, in perfecting life within their own system, in solving their own deep questions of physics and consciousness, than in spending enormous resources sending ships to visit other ordinary star systems. The economics of exploration may simply never favor interstellar travel over local development, regardless of how much energy is available. This idea, sometimes called the Transcension hypothesis, remains genuinely debated, but it adds one more quiet voice to the growing chorus of reasons why even the most advanced civilization imaginable might never come here. The barriers are not human. The barriers are universal. They apply to carbon-based life, to silicon-based life, to any form of intelligence that occupies physical space and manipulates physical matter. The universe wrote these rules before any civilization existed to read them. And it has never, in 13.8 billion years of cosmic history, offered anyone an exception. We have traveled far together tonight, through the illusion of a flat sky that makes the stars look reachable, through 25 trillion miles of nothing that separate us from the nearest neighbor, through an interstellar void so empty, so cold, and so dark that the word emptiness barely begins to describe it, through the electromagnetic silence that keeps Earth invisible to any civilization beyond a razor-thin shell of nearby stars, through the crushing energy costs that make even the simplest interstellar probe effectively unaffordable, through the tyranny of a rocket equation that grows more brutal with every kilogram added to the load, through the ceiling of antimatter, the most perfect fuel physics allows, still impossibly scarce and impossibly expensive, through the broken promise of laser sails that eliminate one barrier only to introduce 5 more, through the slow cruelty of time that erodes crews, ships, missions, and the civilizations behind them, through the cascading biological, social, and mechanical failures that turn the generation ship dream into a catalogue of inevitabilities, and through the seductive but ultimately hollow comfort of the advanced civilization argument, which offers the word technology as an answer to barriers that technology did not create and cannot dismantle. Now, we arrive at the final truth, the one that quietly underlies every section of this journey without ever fully revealing itself until this moment. It is not a technical argument. It is something softer and deeper and in some ways more difficult to sit with. It is the truth about entropy, about time, about the brief, flickering nature of civilizations themselves, and about what the silence of the cosmos is actually telling us. Entropy is the universe's most patient force. The second law of thermodynamics states that in any closed system, disorder always increases over time. Order breaks down. Energy spreads from concentrated to diffuse. Complex structures gradually simplify. Hot things cool. Organized things scatter. This law governs every physical process in the universe without a single exception ever observed. It applies to stars and galaxies and atoms and ecosystems and machines and civilizations. Nothing escapes it. Nothing maintains itself indefinitely without continuous energy input. And over long enough timescales, even that energy input eventually fails. For a generation ship traveling 10,000 years through the interstellar void, entropy is not an abstract concept. It is a daily operational reality. Every seal that must hold, every circuit that must function, every biological cycle that must complete without error, and every social structure that must remain coherent enough to keep the mission alive. All of these are organized systems fighting against the universal tendency toward disorder. And the universe is patient. It does not rush. It simply waits. It waits for the seal that cracks under one thermal cycle too many, for the circuit that accumulates one radiation-displaced atom too many, for the crop yield that drops slightly below sustainability in one bad season aboard the ship, for the political faction that gains just enough power to redirect resources away from mission-critical maintenance. Entropy does not attack. It simply collects. Slowly, consistently, across centuries and millennia, it collects everything that organization built. Reliability engineering gives this a precise voice. A system with even a seemingly high annual survival rate of 99.99% still has less than a 4% chance of surviving 10,000 years without catastrophic failure. For a generation ship to have even a 50% chance of completing a 10,000-year journey, every one of its thousands of interdependent critical systems must maintain annual failure probabilities of less than 1 in 144,000. No material known to physics. No engineering tradition known to humanity. No civilization in recorded history has ever produced systems anywhere near this reliable across anything approaching these timescales. And this is not a uniquely human limitation. Entropy applies to alien engineers just as it applies to human ones. The second law does not check the civilization's age before deciding how quickly things fall apart. Now, add the civilizational dimension. See, humanity has existed as a recognizably modern species for roughly 300,000 years. We have had written language for about 5,000 years. Industrial civilization for roughly 250 years. The entire arc of everything we think of as human achievement, from the first cities to the space age, fits inside a window of time so narrow against the age of the universe that it barely registers as a flicker. The Milky Way is approximately 13 billion years old. If that history were compressed into a single calendar year, human civilization would appear in the final few seconds of December 31st. We are extraordinarily brief, and there is no particular reason to believe that any other civilization is significantly longer lived. Civilizations appear to follow patterns. They develop, they grow complex, they face internal pressures from resource depletion, environmental change, social fragmentation, technological disruption, or simple historical contingency. Some collapse, some transform into something unrecognizable, some perhaps transcend into forms that no longer engage with the physical universe in the way they once did. But the window during which a civilization possesses the specific combination of technological capability, institutional stability, and outward-directed ambition needed to launch and sustain an interstellar mission is almost certainly very short, relative to the timescales the journey itself demands. A civilization that develops interstellar launch capability might maintain that specific motivation for a few centuries before either collapsing, transforming, or redirecting its energy inward toward more immediately rewarding pursuits. This creates a probability problem of quiet devastation. The two civilizations must not only exist within communicable or reachable distance of each other, they must exist simultaneously within their respective windows of outward-directed interstellar capability. And those windows, measured against the billions of years a galaxy has been producing stars and planets, are extraordinarily thin. Think of two candles burning in an enormous cathedral. The cathedral is vast, its ceiling lost in darkness, its far walls invisible. Yet each candle burns for just a few seconds. The probability that both candles burn at exactly the same moment, and that the light from one reaches the other before it gutters out, is vanishingly small. Not because candles are rare, but because the cathedral is too large and the flames are too brief. There is a speculative idea that some astrobiologists discuss with a kind of quiet gravity. Perhaps the universe produces intelligent civilizations regularly, as perhaps the Milky Way has hosted thousands of them across its 13 billion year history. Each one rising, reaching for the stars, discovering the same crushing mathematics of distance and energy and time, and then quietly turning inward. Building beautiful things, understanding deep truths, living rich and complex lives within the boundaries of their own solar system. And then, after some centuries or millennia of flourishing, fading, leaving behind no monuments visible at interstellar distances, no signals strong enough to survive the crossing, no ships that ever arrived anywhere, just silence. Not the silence of absence, the silence of isolation, the silence of a universe that produces minds in abundance, but separates them with distances so vast that those minds never find each other. This is perhaps the most important reframe of everything we have explored tonight. The silence of the cosmos is not evidence that we are alone. Loneliness is not the message the universe is sending. The message is something different, something more subtle and in some ways more profound. The universe builds life. It builds curiosity. It builds intelligence and wonder and the deep ache of wanting to know whether anyone else is out there. And then it separates all of those minds from each other with distances measured in light years, at energies measured in the output of stars, and time spans measured in the lifespans of civilizations. It does not do this out of cruelty. It does not do this by design. It does this because it is very, very large. And because the speed of light, fixed at 670 million miles per hour since the first moments of the Big Bang, is simply not fast enough to connect a universe this wide. You exist tonight on a small rocky world orbiting an ordinary star in the outer suburbs of one galaxy among 2 trillion. You are surrounded by an ocean of silence so deep that no signal from beyond it has ever clearly reached you. And somewhere out there, across distances that break every analogy and defeat every calculation, other minds may be lying in their own darkness beneath their own unfamiliar stars, feeling the same quiet wonder, the same reaching ache, the same beautiful and unanswerable question. Are we alone? They will never know about you. You will never know about them. Not because either of you failed, but because the universe is the cathedral, and you are both candle flames, burning briefly and beautifully in your own small circles of light, casting no glow beyond the darkness that surrounds you. And that darkness is not empty. It is simply wider than any flame can reach. Let that thought settle gently now, like dust drifting slowly to the floor of a quiet room. The stars are still there above you, still wearing their ancient lie of closeness, still glittering with a beauty that belongs entirely to you and to this moment. You are small, and you are brief, and you are here, breathing, warm, alive in a universe that may never fully know itself. Let your eyes grow heavy. Let the weight of the cosmos rest softly on your chest. Let the silence between the stars become the silence of your own rest. You have traveled far enough tonight. The void can wait. The questions can wait. Everything vast and cold and unreachable can wait just a little longer while you sleep. You are here. That is enough. That has always been enough. The cathedral is quiet now. The candle flame that is you burns softly in the dark, small and warm and present. All the mathematics of impossibility, all the crushing distances and staggering energies and relentless passing of time, they recede now like a tide pulling slowly back from shore. What remains is simpler, warmer, the feeling of being alive on a pale blue world wrapped in air and water and the accumulated warmth of 4 billion years of biology finding its way toward this moment, this breath, this heartbeat. The stars above you are not unreachable destinations tonight. They are simply beautiful, and ancient light that traveled unimaginable distances to fall softly on your sleeping face. Let it fall. Let the universe be large and let yourself be small inside it. Not diminished by the scale, but held by it. The way a single note is held inside a vast and quiet piece of music. Rest now. The cosmos will still be there when you wake, and so will you.